In this video, we're going to just briefly introduce the simplex algorithm that is used in solver. Using the simplex method, we first convert all the inequalities to equations by adding slack variables to the less than equal to constraints and subtracting excess variables for those greater than equal to constraints. Okay. For example, if our constraints look like this, those A's represent numerical values. We know that for linear programming models, our constraints take the format with some numerical values multiply our decision variables plus minus them together. And so that's like the left-hand side. So it's a linear combination of some numerical values and our decision variables. Okay, so then less than equal to a numerical value on the right-hand side. So for this less than equal to constraint, what we do is we add a slack to make it equal to. So if you think about it, by adding this slack variable, this sk here, to convert this less than equal to constraint to an equal to constraint, we are saying that as long as this slack variable is greater than equal to 0, then it's the same. So this equation is the same with this inequality. Okay, think about it. So as long as we have this s being positive or a 0, then this equation is the same as this inequality. So when this s is 0, then we reach a strict equal to constraint, so will be equal to. When this s is positive, then the left-hand side in this original constraint will be less than this b, the right-hand side. Similarly, for greater than equal to constraint, what we do is we convert it by subtracting an excess variable. So as long as this excess variable, this ek here, is a positive or 0, then this equation is the same with this inequality constraint. So when this z is 0, then this constraint is satisfied at a strict equal to. And when this e is positive, then we know that this left-hand side part is greater than the right-hand side, the b. Okay, so the reason we convert those less than equal to or greater than equal to constraint to equations is that so we can solve them. For example, in this example here, we're trying to maximize this objective function that contains a linear combination of the x1 and x2, our two decision variables, by subject to 5 constraints. And among those 5 constraints, the first 3 are all less than equal to constraints. So we would convert all those 3 constraints by adding a slack variables to them. So it will become this way. The first constraint will add a slack variable s1, make it equal to, and for the second constraint, we add s2, make it equal to, and so on. For the third one, we add s3, make it equal to constraint. And make sure that you add those s1, s2, s3, those 3 new introduced variables to your model to make sure they are greater than equal to 0. Because we mentioned only when those s1, s2, s3 are positive, what we converted, those 3 equations will be the same as the previous model with the less than equal to constraint. If the s1, s2, s3 are not positive, then this converted model is not the same as our previous model, which requires those left-hand side to be less than equal to the right-hand side here. Okay, so remember that this is the right format to convert our models, that you have to have the s1, s2, s3 greater than equal to 0. Now with this, we have 3 equations, okay? And if we have 3 decision variables and 3 equations, then we would be able to solve it. We will get one set and only one set of values for our 3 decision variables. Okay, but now we have 1, 2, 3, 3 equations, and we have 1, 2, 3, 4, 5 variables. How do we solve them? So if there are m variables in a system of m equations, where this n is greater than m, so we have more numbers of variables than the number of equations. We can select any m variables, so the same number of equations, and solve the equations by setting the remaining n minus m variables to 0. So if we look at in the context of this problem, we have 5 decision variables, okay, but only 3 equations. To solve them, we can set 2 of the variables, 2 of the decision variables. So we can consider S1, S2, S3 are our decision variables too, okay. So we can select 2 of the decision variables to be 0, okay, and solve for the rest 3, because we have 3 equations. Then you can imagine if we just pick 2 out of 5 every time to be 0 and solve the next 3, then we can get several sets of values for our decision variables. And then using this method, we'll be comparing. It's kind of like enumerating counterpoint method. So we would comparing every time when we move to one point to the other one, we will look at what the objective function value is, and then we can compare them and solve the problem by selecting that set of decision variable values that gives us the best objective function, which is to maximize this 350x1 plus 300x2. Okay, with that, you can probably think, well, we want to maximize this object function with x1 and x2 in it. So obviously, we won't set our x1 and x2 to be 0, right? If they are 0, it's basically not the maximization problem. But how do we get started? Now, using Simplex method, we start from the 0, 0 value, okay? So the x1, x2, 0 value, and set those to be 0 first, solve for the slack. And with that, obviously, this is not the optimal solution. But we would start from here, and we will switch one of the decision variables that we try to solve, and we call those the basic variables. Okay, so the basic variables, so this group, the basic variables are the ones that we try to solve, and the non-basic variables are the ones that we set to be 0. You can see x1, x2 here, so these are to 0. And then when we set x2 and s2 to be 0, or x2 and s2, they are 0. So we select m minus m variables to be the non-basic variables and set to be 0. Then solve the rest, which is the m, which equals to the number of equations you have, basic variables. And we would that if you think about those, they look like something here. So we start at this point when we set our x1 and x2 to be 0, to be non-basic variables, and then we start to switch. For example, if we switch to this point here, then that means we're going to switch x1 to be a basic variable to be solved. So x1 will no longer be a 0. It will be solved, and here, if we look at it, it gets solved to be 174. And in this case, x2 is still the non-basic variable. So when we switch from one point to another point, we switch one of the basic variable with another non-basic variable. So in this case, x1, x2 are both non-basic variables, but when we move to point 2, we switched x1 out to be solved. And S2 end up being a non-basic variable. So the simplex algorithm deals with when you start from this point, do you go to point 1 or do you go to point 5? Okay, so that's the first thing. Whether you go to point 2 or you go to point 5 depends on which gives you the fastest improvement to your objective function value. In this problem, we're going to maximize our objective function. So if going to point 2 will increase our objective function value more than going to point 5, then we would go to point 2. Otherwise, we're going to go to point 5. And the algorithm also helps us decide which non-basic variable to switch with a basic variable. So when we start from this null point, which is 0, 0, we set our decision variables to be the basic decision variables that we try to solve from the original model to be 0. Okay, and then we decide to switch one of them. So if we decide to move to this 2 point, that means we're going to switch x1 out. Okay, but if we move to x2 if we move to this point 5, then that means we decide we're going to switch x2 out as a basic variable. Once we decide, for example, say we're going to switch x1 out, then which basic variable we're going to switch with x1? Should we switch s1 to be a non-basic variable when we switch x1 out? Or should we use s2? Or should we use s3? So in this case, we used s2. But what's the reason? How do we do that? Why do we choose s2 instead, not instead of s1 or s3? That's what the simplex algorithm also deals with. So using the simplex method, we identify any basic feasible solution or the extreme point. Now we have learned the graphical solution to LP models. We know that the optimal solution always occurs on the corner point. Okay, so if you have alternative solution that's like one edge, but those two corner points are still the optimal solution. So we know that we're going to identify the extreme points, and those extreme points represent the basic feasible solution. Then we move to an adjacent extreme point if such a move will improve the value of your objective function. So if it's a maximization problem, if you move from this current point to an adjacent point, your objective function value will increase, then we will do that. And if we have two directions, say two adjacent points to move, then we're going to decide by moving to which point will our objective function value get improved the fastest. Then we'll choose that direction to go. Okay, so moving from one extreme point to an adjacent one occurs by switching one of the basic variables, meaning those ones that we try to solve, with one of the non-basic variables, meaning those ones that we set to be 0 to start with, to create a new basic feasible solution. Now, when no adjacent extreme point has a better objective function value, we will stop. We will know that the current extreme point is optimal. Okay, so going back to this graph here, suppose we started from point 1 and then we went to point 2, okay? Then from point 2, we would stand here and evaluate. I have two adjacent points. One is 3, another one is 0. By going into which direction will I help improve my objective function value? So we will move, say, to point 3. And when we come to point 3, we will decide again. Standing at this point, I have two adjacent points. One is point 4, another is point 2. By moving to which direction will I improve my objective function value? Or if neither direction helps improve my objective function value, then I will stop. And I will decide that this point is my current optimal objective function we will decide that this is our current optimal solution point. Then we will stop there. So in the Simplex method, we convert the LP model to a standard format. For example, like we said, you add a slack variable to the less than equal to constraint, and you subtract excess variable to those greater than equal to constraints. And then we obtain a basic feasible solution, if possible, from this standard form. We usually start from the null point, which is we set the decision variables to be 0. And we determine whether the current basic feasible solution is optimal. This means that we look at the two adjacent points and see if by moving to either direction will help us improve our objective function value. If not, then the current point is optimal. If yes, then we'll go to the next step. So if the current basic feasible solution is not optimal, we're going to determine which non-basic variable should become a basic variable to find a new basic variable with a better objective function value. So we first decide, should we move, and which direction should we go? Okay, and that is to decide which non-basic variable should we switch out, and then who should we switch with this. And how do we do that is use the elementary row operation to find the basic variables. Then we go back to this point step 3 to determine if we reach the optimal. If not, then continue. So this is the example. You don't have to know how to calculate it. Okay, I'm just showing this to illustrate how do we use the Simplex method. What you need to know is that, first of all, when a standard LP model is given, you need to be able to convert it to the standard format. For example, in this one, we have less than equal to constraints. Okay, all of those are less than equal to, except for the non-negativity constraint. So this is pretty easy. We add slack variables to convert all those 4 constraints to an equation. So this step is required. You need to know that. So when I give you a standard LP model, you need to know, okay, so maximization, we're going to maximize, put this object function to be equal to a z, okay? And we add 1, 2, 3, 4 slack variables to convert those inequalities to equations. And then the next thing you need to know is we count how many equations do we have. 1, 2, 3, 4, not including the objective function. Okay, the objective function is something we're trying to decide to improve its value. So we only solve using the constraints, converted equations. So now we have 4 equations. What does that mean? 4 equations means we can solve for 4 basic variables. Okay, now we have 1, 2, 3, 3x and 4s. So in total, we have 7 variables to solve. 7 variables and 4 equations. So we're going to have 4 basic variables to solve while setting the other 3 as 0. So we have, as we mentioned earlier, to start, we usually start with setting our x1, 2, 3, those 3 decision variables from the original model to be 0. So that's our starting point. If you think graphically, this would be like a 3D coordinate system, and we would start at that 0, 0, 0 point in the coordinate system, and we will decide to move to adjacent corner point. So that will be like a space, okay? But in the space, we still have corner points. So we'll decide to move from that 0, 0, 0 point, which adjacent direction should we go? And that means which x we will need to switch out from being a non-basic variable to a basic variable. And who should we switch with? Should we switch with S1 or S2, S3, or S4? And that is in the Simplex method. So we convert it into this format. then we determine the basic variables. So we'll use S1, S2, S3, S4 to start with. Those four will be our basic variables, while setting the non-basic variables as x1, x2, x3. So these three will be 0. Then we start from this origin point, okay? And the objective function value is, of course, it's 0 because all of our three decision variables are 0. So our objective function value currently is 0. And at every step, we determine, is this our current optimal solution? So it represents this point here, okay? And we're going to just continue. We're going to put those in table format. So this part is not required. You don't have to know how to convert them into the table format. So for this part is just for your information. For anyone who knows about operations research, you need to have a basic idea of the simplex algorithm and how it is used. So we would convert the objective function. So this part, okay, we'll convert this z part by moving this right hand side to the left. So we'll convert into this format. Z subtract those numerical values, multiply your x equal to 0. And put equations including the objective function in this format into a table. Okay, and so for all of the objective function and all the constraints that change it into equations, we will have their coefficients, right? And we'll have their right hand side. We also have the basic variables. Now the z, s1, s2, s3, s4, they are basic variables. And x1, x2, x3, they are non-basic variables, which has a number of value of 0. So we're going to start. So that's the first step. We put them into this table format. We're going to list, we have several rows. So row 0 represents our objective function row. And the row 1, 2, 3, 4 represent our constraints, because we have 4 constraints, right? And we would put in each row the coefficient of our variables in that function. For example, we converted our objective function to be z subtract 60 x1 subtract 30 x2 subtract 20 x3 equals to 0. That's the right hand side, okay? So that's those are the coefficients we put in this table. Similarly, if we read here, we can tell the constraint is 8 x1 plus 6 x2 plus 1 x3 plus 1 s1 equal to 48. That's our first constraint. The second constraint would be 4x1, 2x2, 1.5 x3 plus s2 equals to be 20. 2x1, 1.5 x2, 0.5 x3 plus s3 equals to be 8. And the last one, x2 plus s4 equals to be 5. So this was the model that we created by converting the less than equal to constraint into equations, right? And this is how we put them into a table format. We basically just list the row numbers, list all the decision variables that we have, and the right hand side, we put their coefficient in this table. And for each row, we would specify what the basic variable is in that row. You see that we usually use the variable that has a 1 as coefficient in that row as the basic variable. So the z is the basic variable here. And in the first constraint, we added s1. S1 had this 1 as its coefficient, so S1 is the basic variable. S2 is the basic variable in the second row, S3 third, and S4 in the fourth row. And from here, we would perform elementary row operation to find a new optimal solution. Because we know that this z equals to this, that's our objective function. Okay, to maximize this z, we would increase x1 first. Okay, when we compare x1, x2, and x3, x1 has the largest coefficient, 60. So that's why increasing x1 will help us improve our objective function value the most. It will improve it the fastest because its coefficient here is 60. By increasing x1, x2, or x3 by the same unit, for example, by 1, x1 can increase the objective function value by 60, while x2 can only increase our objective function by 30, and x3 can only increase it by 20. So we would decide to switch x1 out of the non-basic variable group, make it a basic variable. Because we know that when we make it a basic variable, its value will increase from 0 to a positive value. So we decide to move in the direction that goes to x1 being a positive value now. And then we would do a ratio test, which I'm not going to go into details, to make sure that we choose the right non-basic variable to switch. To make sure we choose the right basic variable among S1, S2, S3, S4 to switch our x1 to. You see, when we switch x1 out of the non-basic variable group into the basic variable group, we need someone from the basic variable group to come out, right? And which one should that be? Should that be S1 or S2 or S3, S4? We perform a ratio test to determine that. And in this one, we choose to switch S1 out. And then we continue this table following that steps mentioned earlier. And eventually, we would reach to this last table where we get our z equals to be this. And we find out x2, s2, and s3, those three variables in this objective function all have negative coefficients. That means by increasing either of them, our objective function value will decrease, which is not going to help with this maximization problem. Then we stop there. And we will conclude that our optimal solution is what we found here. And our optimal objective function value is this 280 here. Okay, so that's just a very brief introduction to the simplex algorithm. As I mentioned, so what you really need to know for this class, okay, is to know how do you convert a given LP model into the standard format by adding slack variables to less than equal to constraint and subtract excess variables to greater than equal to constraint. And know that by counting how many equations do we have, not including the objective function, that's how many non-basic variables you will have and how many basic variables you will have. And know that graphically, using this, just think in your mind that we start from this origin point, this 0, 0 point. If we have like, say, 4 decision variables, then we would start from that 0, 0, 0, 0 point, though we can't really draw it. But that's the origin point that we start by setting our decision variables to be 0, and then continue with switching one of them out from the non-basic variable group to be a basic variable, right? And switch with one of the basic variable into that non-basic variable. So that represents from that origin point going to an adjacent point in that feasible space.